Thank you for joining us today. I'm pleased to present. Our presenter is Robbie Pickering. Robbie Pickering is an environmental engineer with more than 13 years of experience promoting water efficiency and sustainable facility management. For the WaterSense program, he supports the product and home specification development process and has helped develop technical materials to assist a variety of commercial, institutional, and multifamily building types in understanding and implementing water-saving best management practices. So thank you so much for joining us today, Robbie. You can take things away.
Great, thank you. Just confirming you saw the slide change.
Yes.
Okay, great. So yeah, thanks for everyone for joining us today. I'm here to talk a little bit about WaterSense and WaterSense or water saving opportunity in mechanical systems. This is part of a Water Wednesdays series that Energy Star and WaterSense host for commercial and institutional facilities. There are 2 remaining webinars in 2023 after this one, so we encourage you to tune in if you're interested in learning more about reducing water use in commercial buildings. Our agenda for today is on the slide. I plan to focus primarily on water use within cooling towers. However, I'll also touch on best practices associated with single pass cooling and steam boiler systems, and then share a few additional resources at the end. So the WaterSense program was first launched in 2006 to promote water efficiency and encourage innovation in manufacturing. We help organizations and consumers save water for future generations. The WaterSense label, which you can see on the screen, provides a simple way for consumers and businesses to identify water efficient products, homes, and programs. The label helps consumers identify products that have been independently certified for both water efficiency and performance. And the label is generally reserved for products that will reduce water use by at least 20%, as well as and perform as well or better than standard models. We label a variety of residential commercial products. To date, there are more than 43,000 product models that have earned the WaterSense label in 8 different product categories. This includes indoor plumbing products like toilets, urinals, shower heads, and faucets, irrigation products like irrigation controllers and spray sprinkler bodies. We're also currently working on new specifications for irrigation sprinkler nozzles and point-of-use reverse osmosis systems. More information on how each of these products can save a facility water is on our website. We also work really closely with Energy Star to make sure that water factors are included in their specifications and to consider energy savings in ours. So for example, if you look for Energy Star certified clothes washers, dishwashers, ice machines, and combination ovens, these all are also more water efficient than their standard models. So within commercial buildings, water use can vary depending on the building type. Knowing exactly how your building uses water and where it consumes the most will really help you prioritize your efforts and look for potential efficiency opportunities. Understanding water use can be done by tracking your water meters and sub-meters, by conducting a more detailed water assessment and developing a water balance. We don't have time to really get into this process today, but we do have previous Water Wednesdays webinars on the topic, or you can use some of the resources that I'll share at the end of this webinar so that you can get a better understanding of your facility's water use. So the chart on the screen is an analysis performed by WaterSense, which shows that consistently water that's used for heating and cooling can really account for a significant amount of a facility's water use. Buildings with high process loads, particularly hospitals, laboratories, data centers, manufacturing sites, they often require a lot of cooling and then as a result have really high water use. While not all facilities have cooling towers, if your facility does have one, there's a really good chance that it makes up a significant proportion of your facility's water use. There are a variety of reasons that facilities should be interested in water efficiency, both in general and specific to mechanical systems. First and foremost, as I'm sure you're all aware, saving water can help reduce costs and reduce operating expenses. Water and sewer costs are rising well above the consumer price index with no real signs of slowing down. I think it's higher than any other utility or service that you know have for your facility. Water costs have risen greater than that. Saving water and energy can also help improve equipment efficiency, which often reduces maintenance costs and man hours required for repairs. Saving water can also save energy used to pump, treat, and heat water. This water energy nexus is an important concept within mechanical systems, especially. 8% of commercial buildings energy use is actually to heat water, about the same amount of energy that's used for cooling and ventilation. Therefore, there's a really large energy savings opportunity by reducing hot water usage in mechanical systems, in commercial kitchen equipment, and laundry and sanitary systems. Overall, evaluating water and energy efficiency together really provides the best results and the greatest resource for cost savings. And actually, we have the next webinar that we have in November covers the energy water nexus. So I encourage you to sit in if you're interested in more opportunities for both energy and water savings. And then finally, saving water in your mechanical rooms really tends to be a bit of a behind the scenes conservation effort. There's times where more forward facing efficiency projects like restroom upgrades or landscape replacements may not be pursued just out of fear that there might be backlash or customer dissatisfaction with the end result. Mechanical improvements can have significant water savings and cost savings without really impacting building occupants. So if you've sat in on any of WaterSense's webinars before, you'll know we like to suggest that you just add water. Saving water is really not much more difficult than saving energy. It just often requires a little bit of extra focus. Most of you have been managing energy for many years. It's certainly an even hotter topic now than it was many years ago with regard to greenhouse gas emissions and decarbonization. So with all of that, you likely already have protocols, procedures, and systems in place for monitoring and managing your energy throughout your facility. In many cases, adding water really just requires you to pay attention and to add water efficiency practices to your standard operating procedures and business routines so that employees are aware of water use, they can understand how water should be being used, and can work towards better managing energy and water together. Often, effective water management just requires someone to, as I said, pay attention to make sure that water waste isn't something that's just written off as insignificant. Leaks and malfunctions can be a sign of a bigger issue, and can also lead to just an ongoing operating expense that really is unnecessary. Similar to with Energy Star, we also suggest adding WaterSense or water efficiency requirements in all of your procurements and purchases as you might do with Energy Star. Monitoring water bills and meter data, such as within Energy Star Portfolio Manager, is also a great first step to water management. Just making sure that someone's reading bills or reading meters and logging it regularly to see what trends are and to identify potential leaks and anomalies. So in that vein, water meters are really a vital tool in tracking and measuring water use within the facility. You want to make sure that each of your sources of water is metered and tracked separately. In some facilities, there's only one master meter for the entire building. So it can be really helpful to also install sub-meters on major water using areas or systems. This can include tenant spaces, cooling towers, irrigation systems. It's a lot easier to spot areas to reduce water use, or where something might be going wrong when you're accurately measuring and monitoring it. One thing to note is that sub-meters do not need to have separate utility accounts. Sub-meters are mostly used by facilities or facility managers to manage their water use internally instead of waiting for a monthly or a quarterly bill. This can help cut your response time and save money in the long run in case there's a leak or malfunction. There's also many flow monitoring devices on the market that can be easily connected to existing building automation systems or energy management systems that can help send alerts if there's a leak or other irregular water use detected. specific to mechanical systems, large mechanical systems that use a lot of water, such as cooling towers and steam boiler systems, are a really great place to include separate sub-meters to track your consumption so that you understand how these systems use water. Another upcoming webinar in December, WaterSense and Energy Star are hosting one on water submetering. And so again, if you're interested in finding out more about this specific topic, you can tune in December. So I mentioned Energy Star Portfolio Manager earlier. This is a really great resource for tracking and monitoring your water bills and meter readings on an ongoing basis. Portfolio Manager allows building managers the opportunity to track energy use, water use, and waste. You can track water use on the Portfolio Manager's water tab, add your water meters like you would any other utility meter, and then begin entering your water use data. You can also select whether this is a sub-meter of the main supply so that you're not double counting water use. And another reminder is just to be sure to pay attention to the units that the meter uses, just to make sure that you're not causing conflict between how you're reporting water use. Another good starting point, and just one overarching recommendation for any facility before you undertake a major water efficiency project, is to call your utility. It might sound counterintuitive, but there's many water utilities who are really interested in helping you save water and offer a range of services that can be immensely helpful. This may include providing historical water use data for your facility, offering expertise or assistance in conducting a water assessment. Some utilities may even offer to pay for it. Some utilities offer a deduction on wastewater rates for any water that is not sent to the sewer, such as water that's evaporated from a cooling tower or used for irrigation. Your utility will be able to explain the metering or reporting requirements to earn this sewer deduction. Utilities can also communicate other rebates or incentives that they offer for replacing equipment or implementing water efficiency upgrades, including for major mechanical systems. They can sign you up for leak alerts so that they can reach out when they suspect a leak. And lastly, they may be able to point you to preferred vendors in your area with expertise in water efficiency and who have experience navigating their rebate programs. So I heard about this on another WaterSense webinar from Aniki Chamberlain of Miramar Water and really liked it, so I thought I'd share it here as well. As a general approach, and especially when we're talking about expensive mechanical systems, it's really beneficial to follow an efficiency hierarchy to help make water efficiency more manageable and also more cost-effective for your facility. The first step is to really make sure your equipment is running as it's intended and designed. If you identify leaks or broken or malfunctioning equipment, it's best to get those repaired as soon as possible. When you're dealing with systems that rely on sensors, valves, or other mechanical equipment, there's always a chance that there's a mechanical issue that's going to present itself and get in the way of proper operation. So investigate and repair those issues whenever they come up. Second, once everything is working as intended, you can then consider low and no cost adjustments to the system to achieve water efficiency. Oftentimes, there are easy opportunities to make simple adjustments to controls or operating procedures of a system that don't necessarily require a major investment. For example, for a cooling tower, it may be possible to change the settings on a conductivity controller so that it blows down less frequently while still operating within the acceptable range for the cooling tower. The third level of hierarchy is to make sure these processes are becoming a routine. So make water management activities such as monitoring your water use and confirming operation of equipment on a regular basis part of someone's routine and part of their job description. You can ensure that by doing this, you can ensure that your equipment is really operating efficiently on an ongoing basis. And then lastly, only after you've conducted your repairs, made some operational adjustments, and improved the routines so that the system's operating efficiently at all times, then you should consider a major upgrade. Upgrading equipment is often where people want to start. However, this can often be a major stumbling block because the capital expense of these major improvements can be very limiting for a lot of facilities. So while things like using alternative water sources or implementing a major technology change can have very real water and energy savings benefits, it often ignores the fact that much of these savings may be able to be achieved by just optimizing your operations of the existing equipment. So with that, I'm now going to just talk through some of the major areas of mechanical water use in most commercial facilities. Water is commonly used as a heat transfer medium in various systems used for heating and cooling. These systems include single pass cooling, chilled water systems, and cooling towers and steam boilers. So single pass cooling, if present, has the potential to be the single greatest water waster in a facility. When looking for savings opportunities, this is a really good place to start. So single pass cooling is a situation where city water is plumbed to a piece of equipment to remove heat. This is typically a motor or a compressor. After the water goes through, it goes right down the drain. In a commercial facility, you might find this associated with an air conditioning unit, walk-in freezer or refrigerator, ice machines, vacuum pumps, or medical equipment. This cooling method can use 40 times more water to remove the same heat load as a cooling tower. So you can see why it's important to get rid of. If possible, as I said, just get rid of it. You can do this by either replacing water-cooled equipment with air-cooled equipment or by providing cooling water from an existing chilled water loop. There are typically significant cost and water savings available for these changes. In cases where you can't eliminate single pass water use, make sure that your system is using the absolute minimum volume needed. Check the equipment specifications and make sure that you're getting the temperature rise in the water that you're applying. Also make sure that the water turns off when the motor or the compressor isn't running. This is often controlled by a solenoid valve so that it activates or it shuts the valve when the motor or the compressor is no longer running. But in some cases, this valve can fail and it allows the water to flow at all times. So this is something, a maintenance item that's worth checking up on and that often needs attention. In some cases, single pass cooling water can be collected and reused for another purpose, but it really is just best to eliminate it before its use. These photos illustrate the potential magnitude of savings opportunity, particularly in setups that have a continuous flow of water. On the left, we have a flow of 1 gallon per minute, which would consume more than 500,000 gallons of water per year and cost about $5,600 at average water and sewer costs. And then at the right, you can see the flow equivalent of a garden hose at full flow. If that flows 24/7, it would amount to more than 3 million gallons of water use and cost more than $33,000 a year. So fortunately, most facilities that have substantial cooling loads use recirculated chilled water systems. Chilled water systems typically have several key components. They have a heat exchange unit. These are supplied with chilled water that are providing either space cooling or in some other equipment cooling. This is where the heat load comes from. The chilled water takes that heat load and directs it back to the chiller. Typically, chilled water loop is a full closed loop, and therefore you should be seeing very little water loss or consumption in this chilled water loop. It's good practice to have makeup water meters on the chilled water loop so that if you see any consumption or continuous makeup, you can identify that you likely have a leak and you can get it resolved. So the chiller unit is what generates the chilled water through a refrigeration process. The chiller transfers heat from the chilled water loop to the condenser water loop, which heats the water. And then lastly, the condenser on the refrigeration cycle may be either air-cooled or water-cooled. Larger units tend to be water-cooled using a cooling tower, as shown here. Water is evaporated from the cooling tower. We're not as concerned with air-cooled models from a water efficiency perspective, so we're going to get into more detail on cooling towers now. That condenser unit or cooling tower then cools the water and returns it to the chiller. So that we have everyone oriented on cooling towers, I just want to take a moment to go over some of the basics. The concept is fairly simple. Water and air flow past each other, typically in a countercurrent or cross-flow configuration. In this schematic illustration, hot water from the chiller is introduced at the top of the tower by spray nozzles and they flow down along a fill material while air is drawn up through the tower by a fan. As the air passes over the water, some water is evaporated, which removes heat and reduces the temperature of the water in the tower. The energy lost via water evaporation helps remove heat from the system, and then this cooled water is then returned to the chiller to collect more heat. So the cooling tower has a number of inputs and outputs that help explain how water is being consumed in the system. So first, there's, as I mentioned, this circulated cooling water loop that is introduced into the tower to be cooled. The water is removing heat from a piece of equipment and is then returned to, in this case, a chiller, and it returned to the chiller once it's been cooled in the cooling tower. Some of this water is evaporated to remove heat. This is by design and is the purpose of the cooling tower. Some small quantity of water is often lost via small water droplets that spray from the tower. This is called drift. Some water is discharged as blowdown to keep minerals from building up in the recirculating cooled water loop. The cooling tower water loop or the condenser water loop. And then makeup water is added to balance the losses due to evaporation, drift, and blowdown. And we'll talk about each of these in a little bit more detail now. So now that we understand what's going into the tower and what's maybe leaving the cooling tower, we can understand where there are opportunities to save water. So there's a few options. We can either reduce the evaporation heat load on the cooling tower. We can reduce drift losses, reduce system blowdown. We can minimize the propensity for leaks, which are really just another form of unintentional blowdown. And then we can provide makeup water from a source other than city water. So because evaporation is the primary function of a cooling tower and how most of the heat is carried away, this really isn't the focus of our water efficiency efforts. Based on the thermodynamic properties of water, 1.5 gallons of water per hour are needed to be evaporated for every ton of cooling that is offered. So, and this number is fixed. So you're always going to use 1.5 gallons per hour per ton. Since we want that cooling to occur, we're not trying to limit evaporation at all. That being said, anything that you can do to make your chiller plant more energy efficient will also lower your cooling load and thereby reduce the amount of water needed for evaporation. So aspects of your facility that may impact your evaporation load include building design and envelope, HVAC design and equipment selection, lighting and plug loads, occupancy, operating characteristics, and maintenance practices. So for example, a lighting retrofit or system efficiency upgrade or really any other energy efficiency project can have a commensurate water savings as well from your cooling tower. So beyond water that is evaporated, some water can also be lost to drift or splash out. In a well-designed tower equipped with drift eliminators, this should really be minimal. However, if you're near your tower and you're noticing visible droplets that are exiting or kind of pooling of water outside, this may be a sign that your drift eliminators need some attention. Drift eliminators can be added to an existing tower. You can also get higher efficiency drift eliminators to replace older, poor performing ones. They also have ancillary benefits as well, such as helping to reduce risk from Legionella or cooling tower water being sprayed in the outside environment. The other maintenance item to be aware of is the cooling tower overflow. Most towers are equipped with an overflow drain that prevents it from being overfilled in the event of equipment malfunction. If the level sensor or a fill valve or makeup valve in the tower fails, this can cause an overflow to the drain without the facility staff realizing it immediately. So the tower on the slide, or the photo on the slide, is of a tower basin where the fill valve controlling the makeup water was stuck partially open. Water was constantly flowing, overfilling the basin and going down the drain. This is a good thing to really monitor during daily rounds. A broken fill or float valve in a cooling tower can easily waste hundreds of thousands of gallons every day, especially if they go unnoticed. So definitely something to check in on. And in short, you should never ever see water flowing to the overflow drain. This is only meant for overflow situations. So if you see water in your overflow drain, check it out and identify the issue and correct it as quickly as you can. So The primary opportunity to improve water efficiency of a cooling tower is really in reducing the amount of blowdown by concentrating minerals in the recirculating system. For background, as the mineral concentration rises in the tower, the blowdown stream will discharge a certain amount of water and replace it with city water, thus reducing the overall concentration of minerals in the system. So mineral control and blowdown is necessary to protect the cooling tower and chiller equipment and to prevent the formation of scale, corrosion, or biological growth. Um, a measure of this efficiency is called cycles of concentration, which is really the ratio of the concentration of minerals in the blowdown to the concentration of minerals in the makeup water. It's also representative of the ratio of makeup volume to blowdown volume. So the higher the cycles you get, the less blowdown is occurring. So if you recall our schematic from the cooling tower, the only water that's being added to the system is from makeup water. When operating properly, the only significant ways water is leaving the system is through evaporation and blowdown. The drift should really be negligible. So reducing the cooling tower blowdown, as I mentioned, is the biggest opportunity for savings. The reason for this is the blowdown is to keep minerals or dissolved solids from building up in the recirculated water throughout the tower. An example of that is shown here. So city water contains dissolved solids. As water evaporates, these dissolved solids stay in circulation and begin to get concentrated over time. If the concentration gets too high, the solids will begin to form scale buildup on the surfaces of the chiller system, which can degrade performance and damage equipment. There's some water that is regularly discharged. This is the blowdown to keep these dissolved solids in check. The blowdown is typically controlled by a conductivity meter or a controller. Careful blowdown control, as I said, offers really the best opportunity for savings in a cooling tower system. So this background establishes the basis for saying that by maximizing your cycles of concentration and reducing the blowdown, your system efficiency will improve. To maintain high cycles of concentration, you can keep minerals in solution by managing the system water chemistry. Minerals are kept in solution by adding chemicals or another treatment mechanism that can control the pH and inhibit scale and corrosion. The target cycles of concentration that is achievable in your cooling tower is based primarily on your facility's incoming water incoming water quality. This table is from ASHRAE 189.1, which establishes maximum values for certain parameters that recirculating cooling water should stay below. This information can be helpful in identifying your cycles of concentration limit. So, for example, if your limiting parameter is total dissolved solids or TDS, you can identify your target cycles by evaluating incoming water quality. If your incoming water quality's TDS is 1,000 ppm, your tower may only really be able to safely run at 2 cycles because 2,050 divided by 1,000 is approximately 2. However, if your incoming water has a TDS of 200, you might be able to achieve 10 cycles of concentration. So calculating that target cycles of concentration and establishing a water treatment program may sound complicated, and it can be. Oftentimes it is complicated. That's why most buildings commonly contract this out to a water treatment vendor. This is someone who comes on site or comes to your facility once every couple of weeks or months and checks up on the water treatment program. They'll take some measurements, they'll monitor chemicals, and make sure that everything is in working order. So when working with a vendor, there are some important things to keep in mind at the onset and throughout your relationship to ensure that you're achieving your goals. First, communicate your goals with respect to water efficiency. We encourage you to work with a qualified water treatment vendor that shares your goal of water efficiency and is willing to work with you to establish a target cycles of concentration based on your local water chemistry and the water treatment options that they're offering. Second, ensure that they're providing you with a comprehensive summary of their service visits. This should include water chemistry information. Your treatment vendor should be taking regular samples of your incoming water quality and the cooling tower water quality to help determine whether the goals that you established are being met. And if they're not providing this information, make sure to ask them to. Third, be sure that you're reviewing the service reports that they provide to make sure that they're achieving the cycles of concentration goals that you've both established together. So sometimes there's very valid reasons why these target cycles aren't being met, such as a mechanical failure. However, sometimes it's just a result of them not paying attention and not doing exactly what you hired them to do. So be sure to request these reports and review them regularly to make sure that they're meeting your goals. And then lastly, you should also try to find a vendor who can really be a partner in your water efficiency. Oftentimes, treatment vendors can be a resource for providing ideas or technology options or cost estimates for increasing cycles of concentration beyond what is achievable with typical chemical treatment. So this is an excerpt from a pretty typical water treatment report. The format of these reports can kind of differ a little bit depending on the vendor, but the information is usually the same. And often the more information you get, the better. So the report includes conductivity on the makeup water and the cooling tower water. This cooling tower water is the same as the blowdown water that gets sent to the sewer. Dividing the blowdown conductivity by the makeup conductivity gives us a little over 6 cycles, which really isn't that bad. One other thing to be aware of, where does your conductivity sit with respect to the control point? So you can see on the right, the control point is 2,750. And in this case, the conductivity of the tower is at 2,755. So right at this upper limit, which is where you want it to be. In terms of retrofits that you can do to get the most efficiency out of your tower, first is to install an automatic controller that controls blowdown based on conductivity to maximize your cycles. You can also install makeup and blowdown meters to track your water use on an ongoing basis and monitor trends, taking corrective action if necessary. I mentioned this earlier, but one important cost-saving measure is that with appropriate sub-metering, some utilities will let you deduct the quantity of water you evaporate from your sewer bill. So these savings can be quite significant because cooling towers are big water users. So the cost savings from a sewer deduction can often be used to offset the upfront costs of installing meters or by installing other control mechanisms. So taking steps to improve water quality, such as side stream filtration or basin cleaning to remove sediment, can also offer efficiency improvements. In addition, water softening, if water hardness is a problem in your area, can allow you to increase your cycles of concentration. Your treatment vendor can often advise you on these types of options. So this chart on the slide shows the type of savings that you can achieve by increasing your cycles of concentration. So you read the initial concentrations on the left across the new cycles on the top. And so, for example, by improving from 3 cycles to 6 cycles would provide a 20% savings in cooling tower water use. And this chart here shows just a water consumption of a theoretical 100-ton tower at various cycles of concentration. And you can see by the shape that as you get higher cycles, there's this flattening of the curve since a greater portion of the water is being evaporated rather than blown down. So as you can see, this threshold point's around 5 or 6. So it's a good target to try to achieve 6 or greater cycles. And everything beyond that is kind of gravy. So I just covered a ton of information and best practices in a short amount of time. So I just wanted to take a minute and summarize some of the common failure points that could lead to water waste or cooling tower damage. As far as mechanical issues, you can have a stuck makeup or blowdown valve. A makeup valve that is stuck open will continually fill and overflow the tower. A blowdown valve that is stuck open will continually drain water, essentially creating a single pass system that also wastes cooling tower chemicals. A blowdown valve that is stuck closed will not be able to remove minerals from the system at all and could actually eventually lead to a scale event. Faulty sensors can have similar repercussions. If the conductivity or the level sensor isn't communicating correctly with the controller or blowdown valve, you could be blowing down too much or too little. Like any system, there's a potential for pumps to fail or pipes to leak. And then lastly, controllers, either for conductivity or a chemical feed system, can malfunction and again result in the tower blowing down too often or not enough. On the operational side, there's common failures include establishing incorrect set points at which the system should be blown down. Similarly, the level sensor in a tower could be installed incorrectly, leading to the tower underfilling or overfilling. The chemical feed system can be programmed incorrectly to apply too much or too few chemicals. Those are just a few examples. And most of these things can be pretty easily identified and resolved just by making sure that staff is assigned responsibility for the cooling tower and understands the basics of what's going on in the system. They don't necessarily need to be a mechanical engineer to know what to look for during regular check-ins or regular daily rounds. They should check the overflow drain to make sure water isn't flowing. They should monitor and record meter readings and use them to calculate cycles of concentration. And they should look at the conductivity meter to make sure the tower is operating at its set point. If they do these three things on a daily basis, you can really understand and identify when something is going wrong so they can be resolved before it wastes a significant amount of water and costs you a lot of money. So another opportunity to reduce the amount of potable water used in a cooling tower is to identify an alternative source of water that could be used to supplement or fully replace city water in the makeup line. Some possible sources of makeup water include reclaimed wastewater that's often provided by your local municipality, rainwater, foundational drain water, and air conditioner condensate. One thing to remember when assessing alternative water sources is that the water quality, quantity, and availability should be considered. So only use alternative sources when you're able to match the quality of the alternative source to the needs of the system. In that vein, air handler condensate can be a really excellent source of makeup water for a cooling tower, particularly if the facility is located in a hot, humid climate. Condensate is water that forms on air handler coils, cooling coils as it heats and conditions outside air. The condensate is typically drained right to the sewer or a storm sewer, but since it's generated in its highest quantity when the load on your cooling tower is also at its highest, it makes an excellent source of cold, clean water. The biggest challenge with this type of project is the plumbing required to get water from the air handler condensate line to the cooling tower. However, if the pipe runs are not too long or complicated, you don't need to make too many well intrusions, that can make the project very cost effective. There's a few example designs that have been incorporated in some of the facilities that I'm familiar with. As you can see, these projects don't really need to be that complex or complicated. They can just involve something to catch the water, a submersible pump to pump it away, and the piping to get to the cooling tower basin. The Federal Energy Management Program, or FEMP, has created a really nice resource to help facility managers determine the potential for condensate capture. As you can see, facilities in the Southeast, Midwest, Mid-Atlantic, they all have really high potential for collecting condensate for these types of projects. That being said, really cost-effective projects can be available anywhere, provided that your air handlers are in close proximity to cooling towers. FEMP also has some really nice maps for rainwater potential, as well as reclaimed wastewater availability, which are two other potential sources of cooling tower. And just to kind of summarize, these are a few facilities I'm familiar with that implemented improvement projects, kind of running a range of different things, some collecting air handler condensate, some improving blowdown control, some finding alternative sources of water like RO concentrate, installing water softening, improving the cycles of concentration. You can see the scale of water savings that can be achieved by looking at your cooling tower and by addressing some of their inefficiencies. So the last mechanical system that we're going to focus on is boiler and steam systems. There are two main types of boilers. There are hot water boilers and steam boilers. Hot water boilers are either open systems, which produce hot water for domestic consumption or laundry operations, or they're a recirculating closed loop system that's used for space heating. Domestic hot water efficiency is mainly related to the efficiency at the point of use. So installing high efficiency faucets, shower heads, laundry systems, or cooking equipment will save water and energy. Recirculating closed hot water systems for space heating, similar to with the chilled water system, they should have very little makeup water demand. So again, you can install a meter just to make sure that you're not losing any water in that closed loop system. But the focus for our purposes for water efficiency is on steam boilers. So this is a very simple boiler sketch to orient everyone. Steam is produced in the boiler and used for either space heating or potentially other uses. Once the steam gives up its heat, it condenses back to water and is often collected and returned to the boiler. Similar to cooling towers, over time, minerals can build up in the boiler and periodic blowdown is required to remove them from the system. Where this does vary from cooling towers is that this blowdown is really hot. And frequently it requires a tempering water stream that is mixed with the blowdown to reduce the temperature below 140 degrees Fahrenheit, so it can be discharged to the sewer. And this is based on local codes. So makeup water is then provided to the makeup to make up for steam losses and the boiler blowdown. The most important feature of an efficient steam boiler system is capturing that steam condensate and returning it to the boiler. The water savings are threefold. First, you're returning this high quality hot water to the system, which both reduces the water use and the energy demand on the boiler system. It also eliminates the need for tempering water to cool the condensate before it's discharged. And lastly, it reduces the frequency of blowdown, since the condensate is high quality water with low mineral concentration. Steam condensate recovery as a result has energy savings. Since the steam condensate is really hot, it requires less energy to reheat and produce steam again, and much less energy than incoming city water that is, usually at, let's say, between 55 and 65 degrees. Aside from installation of a condensate recovery system, the key to an efficient boiler operation is to keep all the components in good working order. You'll want to check steam and condensate, steam and water lines for leaks, and check to make sure that steam traps are functioning properly. You'll want to regularly clean and inspect the boiler water and fire tubes for good heat transfer and tune up the boiler for efficient firing. Make sure steam lines and condensate return lines are properly insulated to prevent heat losses. One area that deserves careful attention and where we frequently see water savings opportunity is with the tempering water application. So tempering water is often applied where the hot condensate or blowdown is discharged to the drain. This could be on a boiler blowdown flash tank or condensate draining from a flash tank on a steam vent. These tempering water flows are frequently controlled by a temperature actuated solenoid valve. If the temperature probe or the valve fails, the tempering water can flow all the time, even when it's not needed. So as we saw earlier, any continuous flow of water can be a big water waster. So make sure you're monitoring this valve on a periodic basis to make sure that it's only applying tempering water when blowdown or condensate is being drained. Alternatively, rather than using tempering water, sometimes you can use an expansion tank or a heat exchanger to cool the hot condensate or the hot blowdown before it is discharged. So this can be another opportunity. And in some cases, you can even reuse this heat from the heat exchanger to preheat some of the boiler makeup. So some concepts presented earlier for cooling towers also apply to steam boilers. You'll want to install and read makeup and blowdown meters. You want to maximize your cycles of concentration by capturing as much steam condensate as possible and by minimizing blowdown. And then again, work with a qualified water treatment vendor that is specialized in water efficiency to help you maximize your cycles while still preventing scaling or corrosion within your boiler system. By working with someone who knows what they're doing, this should reduce the amount of water use, your chemical use, and your overall costs. So WaterSense has developed many technical tools and resources to help with conducting a water assessment, creating a water balance, or otherwise understanding water use and water efficiency opportunities within different building types and within different systems. So cooling towers and mechanical systems are one of those. We keep all of our resources for cooling for commercial facilities on our commercial tools and training section of the WaterSense website. This section of the website houses technical guidebooks, assessment tools, worksheets, checklists, case studies, and links to recorded and other upcoming live trainings. So WaterSense at Work presents our most comprehensive guidebook and provides the most in-depth information regarding a lot of the systems we cover today. This guidebook is really meant to help facilities understand, manage, and reduce their water use. It includes best management practices covering water management planning, water use monitoring. It also has information on specific best management practices for different water uses. So sanitary fixtures, commercial kitchen equipment, outdoor water use, mechanical systems, laboratory and medical equipment. It also has some calculations that can help you estimate water use and water savings from certain projects. And we're in the process of updating many sections of this guide. So some of those updated sections are on our website already, and stay tuned for some more that are coming in the next couple of months. As I mentioned earlier, this is part of a monthly webinar series. Next month's topic is Energy Water Nexus, where we will discuss the energy that's embedded in water in ways that you can save both water and energy in your facility. You can register using the link on the slide. Then in December, we'll be talking about water metering and submetering, which can be powerful tools to understand and save water. In case you've missed any of our previous webinars, you can also find those recordings here as well. In terms of other resources, there's two that I want to point out. First, there's a tool from the Environmental Defense Fund that is called the Water Management Application or Water Map tool. This is an Excel-based spreadsheet that has three primary components. There's a water scorecard, a water efficiency calculator, and a cycles of concentration estimator. The scorecard helps facilities or companies assess their water efficiency, and then the calculator estimates the water and financial savings from cooling tower upgrades or from implementing free air cooling. We didn't talk much today about free air cooling, but this is a concept of using outside air that is at low temperatures to assist with cooling loads. Using free cooling can reduce your facility's energy and water use. And then finally, the cycles of concentration estimator takes information about your water quality and estimates the recommended maximum cycles of concentration for your cooling tower. So we talked a little bit about that earlier of how to calculate your target cycles. This is a tool that can help do that for you. Another great resource that is available is from the General Services Administration through their Green Proving Grounds. The GSA, obviously a big property owner, they evaluated a number of alternative water treatment technologies for cooling towers to try to validate vendors' claims on savings, efficiency, and other benefits. GSA summarized their findings in a detailed report. I think they looked at 4 or 5 systems, and some of them have really significant potential to reduce blowdown and increase cycles of concentration. So I look to this as a really great independent source on kind of validating some of those claims and looking for some unique opportunities to improve the water efficiency of your tower. So to kind of summarize, we covered a lot of ground today. So I just want to kind of go through some things you can do right now to get started in making your mechanical and HVAC systems more water efficient. First, check that any single pass cooling equipment is set to use the minimum flow rate required for cooling in all instances, and start investigating alternatives to replace these single pass systems. Install and read meters on all your makeup water lines to your cooling towers, boilers, and chilled water loops. Install blowdown water lines on your cooling towers and boilers. And also, if you have a condensate return system, you can install a meter there as well. Create a daily punch list or rounds checklist for assigned staff to monitor the overflow drain, meters, and cycles of concentration to make sure that the cooling tower is operating correctly. As I mentioned, doing these three things can really prevent a lot of water waste that occurs from a malfunction or mechanical issue that arises. Next, contact your utilities to see if they have any programs that could help you save water and money. This includes the sewer deduction credits, rebates, or assessment support. Take a minute to review the water chemistry reports that are generated by your water treatment vendor to understand what your current cycles of concentration is, and if your target cycles can maybe be adjusted. If your water chemistry allows, work with your vendor to increase your cooling tower cycles, targeting that 5 or 6 threshold. And then lastly, just take a look at the configuration of your facility to see if you can, if there's an easy way to route condensate from your air handlers back to the cooling tower as makeup water. Again, this can be a really pretty simple and cost-effective way to minimize the amount of potable water you're using. With that, I'm gonna open it up for questions. If you have any looking for additional information or questions about either Energy Star or the WaterSense programs,